Hi everyone, welcome to Integral Calculus. Today we explore lesson 8.1 arc length of a curve. Number 1, deriving the arc length formula. Let's say we have a curve that is going like this. Fx. We want to figure out how long is it from this point to this point. What is the length? In order to do that, you're going to take a small arc length is the ds, and we're going to blow it up. So if we blow it up, then we would have something like this, approximately. And we can approximate this ds by sketching out a right triangle. This the horizontal length is a small change in x dx. The vertical length is a small change in y dy. So as you see, we can relate them. ds is using the Pythagorean theorem, ds squared is dx square plus dy square. And so ds would be the square root of dx square plus dy square. If the function is written in terms of x, then dy here can be written as f prime x times x, because f prime x is dy over dx. We have a dx square plus f prime x dx square. And so we can factor the dx square which gives us the f prime x square plus 1. Well, we can take the square root of dx square, and that will give us the square root of f prime x square plus 1 dx. And if the function is written in terms of y, then that would be something like g prime y square plus 1 dy. If the curve is written as gy, then ds could be square root of g prime y square plus 1 dy. Okay, we have the length up a very small arc on the curve. So in order to figure out the arc length from, let's say, x equal a to x equal b, we just have to add up all these small arc length. And when we sum them up, many of them, that would be the limit of the Riemann sum, which is the integral. So the arc length L is the integral from a to b of ds. And this would be the integral root of f prime x square plus 1 ds, yeah, from a to b. A nice way to write out the arc length is just the integral over the curve C, and this part is the curve C. Let's take a look at example. Two computing arc lengths. Example, find the length of the curve y equal root 1 minus x squared from x equal -1 to x equal 1. You can sketch it out, get a visual. X, y. -1 to 1. And this would just be the upper half of the circle. But we know how to figure this out using the circumference of a circle. However, we're gonna use the formula that we just derive to get the same answer. Okay, so from here, take a sample arc. And the sample arc is ds, and that would be square root. This function is written in terms of x, so this will square root of f prime x square plus 1 dx. The derivative is root 1 over 2 1 minus x squared times -2x. Then we're going to square it plus 1 dx. Simplify this and we have a x squared over 1 minus x squared plus 1 dx. Well, do a common denominator. Then it's going to be 1 over 1 minus x squared dx. And this would be root 1 over root of 1 minus x squared. So it's 1 over root of 1 minus x squared dx. Wow. Now we can figure out the length from -1 to 1. That would just be the integral from -1 to 1 of ds. A lot of people would write integral over the curve C ds. -1 to 1 sub ds for 1 over root 1 minus x squared dx, and ta-da! The antiderivative of 1 over root 1 minus x squared is arc psi. If 1 to 1, arc psi of 1 is pi over 2, and arc psi of negative 1 is negative pi over 2, which give us pi. Example, find the length of the curve y equal x squared from x equal to 0 to x equal 1. It's the length of the parabola x, y, right? So it's going to be from here to here. Yeah. Same thing. We're going to take a look at a sample. ds is root of f prime x square plus 1 dx. And this would be root of 2x squared plus 1 dx. So we have root of 4x squared plus 1 dx. Yeah. The length of the curve is integral over the curve C of ds, which is the integral from 0 to 1 root of 4x squared plus 1 dx. Oh, root of 4x squared plus 1. We have to use the trig substitution. X equal 1 over 2 tangent theta. Meaning that dx is gonna be half of secant squared theta d theta. And from here you see that 4x squared plus 1 is root of tangent square theta plus 1. Tangent square plus 1 is secant square, so this would just be secant theta. Okay. With the trig sub, we have, oh yeah, we have to change the limit too, because we have an upper limit and a lower limit. Upper limit would be tangent theta is 2x, so that means the arctangent of 2. If you plug in x equal 1, arctangent of 2, and then the lower limit would be arctan of 0. Well, we know tangent of 0 is 0, which is 0. Okay. Integral from 0 to arctangent 2. Secant theta multiplied to half of secant squared theta d theta. Oh, it is just the integral of secant to the power 3, which we know because we did it before. We did it in section 7.2. Yay. And this is the antiderivative right here. Integral of secant to the power 3x dx. Ta-da. Now let's copy this and use it. So this would be a 1/2 secant theta tangent theta plus ln absolute value of secant theta plus tangent theta. Evaluate from 0 to arctangent of 2. Right? 1/4 secant of arctangent 2. Well, to do that, you're gonna draw out a right triangle. 2, 1, and thus that is root of 5. Secant of the angle is root 5. Tangent of arctangent is 2 ln. Secant of the angle root 5. Tangent of arctangent 2. Okay. Now we sub in 0. Well, tangent of 0 is 0. Secant of 0 is 1. So it's going to be a plus ln absolute value of 1 plus tangent of 0 is 0. Yeah. And then from here, ln1 is just 0. And so simplify this, we have 1/4 2 root 5 plus ln 2 plus root 5. Pretty slick. Okay, one more example. Find the length of the curve y equal x to the power 2/3 from x equal to 0 to x equal 8. First thing is, let's sketch out the curve xy. And this is what it looks like. And as you can see, we have a sharp curve here, meaning that the function is not differentiable at x equal to 0. And so function is not differentiable at x, y equal to x 2/3 is not differentiable at x equal to 0, meaning that we have to look at it from a different lens. We cannot do L equal integral of 0 to 8 and then ds there. Can do this one. We got to write the function in terms of y instead. Y to the power 3/2 equal x. Yay! And then from here, we're gonna look at it through the length of y. So if it's 8, then the output would be y equal to 8, 2 over 3, which is 2 to the power 3, 2 over 3, and that is 4. A sample arc length ds. So this would be, because the function is written in terms of y, it would be square root g prime y square plus 1 dy. And the derivative is the 3 over 2 y 1 over 2 square plus 1 dy. We can simplify this to get one plus 9 over 4 y root 1 plus 9 over 4 y dy. And now we can figure out the length of the curve from x equals 0 to x equals 8. Integral c ds. So because ds is in terms of y, we're gonna have the limit from 0 to 4. Root of 1 plus 9 over 4 y dy. And then we just have to do a simple u sub here. U equal 1 plus 9 4y. Du is 9 over 4 dy. So I mean dy is 4 over 9 du. And ta-da! I'm gonna update the upper and the lower limit also. Upper limit is the plug in y for 4, so it's 10. Lower limit y equal to 0, so it's 1. So integral from 1 to 10 root of u times 4 over 9 du. So 4 over 9 times u 3 over 2 over 3 over 2. Evaluate this one from 1 to 10. 4 over 9 times 2 over 3. We have a 10, 3 over 2 minus 1, 3 over 2, which is 1. And this would give us 8 over 27. Ten to the power 3 over 2 minus 1. Pretty cool, pretty slick. I like it. Thank you for watching. I hope you find the content useful. Please like, subscribe to help the channel grow. I will see you in the next video.